All right, so section 5 is talking about curve sketching, and basically what it does is it puts everything together that we've learned about all of the different derivatives and how it impacts the graph of f. So that's what we're going to be looking at. Generally in this section, you're going to be given the graph of a function's derivative, either the first or second derivative, and we have to interpret that in trying to find information about the original function f. So you can see in this problem, we're given the graph of the first derivative. So we're given the graph of the first derivative. It's defined on the interval from -8 to 8. And we're going to use this graph here to answer these questions. All right, so part A is asking on what intervals is f increasing? So first, we know that f increases when, and so if we're thinking about it in the scope of f prime, we know that f increases when the first derivative is positive. So where's the derivative positive? So when it's positive, that means that it is above the x-axis. So again, remember, this curve is not f, it is f prime. So this curve is above the x-axis, kind of in this region here. Now, technically, it's not above the x-axis here at 3. However, because the derivative is positive on either ends, basically what happens is the function is increasing on that interval, and then it reaches a horizontal tangent, right? So the derivative is 0 there, and it continues to increase after that. So you're going to have a horizontal tangent, and when you have a horizontal tangent in the middle of an interval where it's increasing, if it increases on either side of that horizontal tangent, we can just say it increases through that whole interval. So we can say that at x equals 3, it is still increasing. It still increases through x equals 3. So it's going to be increasing on the entire region from -6 up to 8. So we can say f increases when f prime is greater than 0, and so that's on the interval from -6 to 8. So check for part A. Part B is asking about concavity. So when is the function concave downward? So by the definition of concavity, right, if you remember the definition of concavity, a function is concave down. So f is concave downward by definition when the derivative is decreasing. Now, if we're using the test for concavity, this is also true when the second derivative is negative, right? So if the second derivative is negative, then the function is concave down. But again, we're dealing with f prime here, so we want to know when f prime is decreasing, right? So it is concave down if f prime is decreasing. So where does my function decrease? So it's increasing up until here at about -3, and then from -3 to 3, so in this region right here, you can see that that region decreases and then it starts increasing after that. So my function is going to be concave down on the interval from -3 to 3, let's say. So -3 to 3. So that one's done. Part C. At what x values do we have relative extrema? So remember, relative extrema happen when there's a sign change in the derivative. So for values of x less, so in between -8 and 6, the derivative is negative on that region. It is positive from -6 to 3, and then it's positive again from 3 to 8. So do we have any sign changes in our derivative? Well, we have a sign change at x equals -6. So at x equals -6. And remember, when the sign changes, when the sign of the derivative changes from negative to positive, that tells us we have a relative minimum. So at x equals -6, f prime changes from negative to positive So there is a relative minimum at x equals 6, or sorry, negative 6. So we have a relative minimum there. And that's because, again, the derivative changes signs from negative to positive. And then lastly, where does the graph have an inflection point? So inflection points happen at change in concavity of f. And basically, there's a change in concavity when our derivative changes from increasing to decreasing. Because if you remember, right, we said that by definition, a function is concave down when the derivative decreases. And conversely, our function is concave up when the derivative is increasing. So if we look at intervals where our function changes, where our derivative changes from increasing to decreasing, that's going to be where we have inflection points. So you can see that my function is increasing, sorry, not my function, my derivative is increasing from negative 8 up to negative 3 here. And then it decreases there from negative 3 to 3. And then it increases again from 3 to 8. So where are there changes in intervals of increasing and decreasing? So we have one here at x equals negative 3, and then again at x equals positive 3. So that's where there are changes in increasing and decreasing. So part D, there is an inflection point. I'm going to abbreviate. At x equals negative 3. And this is because, f prime changes from increasing to decreasing. And there's an inflection point at x equals positive 3. Again, because f prime changes from, this is going to be from decreasing to increasing at that point. Okay? And so that's why we have inflection points at x equals 3 and x equals negative 3. Is because the function changes, the derivative changes from increasing to decreasing and decreasing to increasing at those points, which means that our original function f is changing from concave up to concave down, and then to concave down to concave up, which is when we have our inflection points. In the second example, again, we're given the graph of f prime. So you can see right here it says the graph of f prime. We are told that the function f is defined on the closed interval from -1 to 5. The derivative has horizontal tangents at x equals 1 and x equals 3. So that's going to give us information about the second derivative, I guess. And then that our function f, so not this function, but the function f, is twice differentiable with f of 2 equaling 6. So we know that the second derivative exists because it's twice differentiable, which means this function is differentiable. And we can kind of see that from the graph itself, right? It's smooth and continuous, so it's going to be differentiable. Okay, so part A, x-coordinate of each of the points of inflection of the graph. So again, if you recall when we were just talking about points of inflection, when considering the graph of f, that's when when considering the graph of f prime, that's when f prime changes, right? When it changes from increasing to decreasing, and then also from decreasing to increasing. So you can see that f prime is increasing here, and then it's also increasing there, and then it decreases in this region here. So where do we have those changes? So we have an inflection point at x equals 1, and then also at x equals 3, because our graph, and you would want to give justification, right? So give a reason. So the justification is that f prime changes from increasing to decreasing. And this is at x equals 1. And then at x equals 3, f prime changes from decreasing to increasing. Again, this is at x equals 3. And so thus, if it changes from increasing to decreasing, it's changing from concave up to down, and then from down to up here. And remember, when we have changes in concavity is when we get inflection points. Okay, and then part B, we're given the function g defined by g of x equals x times f of x. We want to find the equation of a tangent line. So remember, when we're asked to find the equation for a tangent line, that means we need a slope and we need a point. So we're trying to find the graph, the equation of the tangent line at x equals 2. So first, what is g prime? So g prime, we're going to have to use product rule. So it's the first times the derivative of the second plus the second times the derivative of the first. So this is g prime. We want to know g prime at 2 and then what g of 2 is. So g prime of 2 is going to be 2 times the derivative at 2. So we can get that from the graph. So remember, this is the graph of my derivative. So at x equals 2, my derivative's value is -1. But let me just kind of write out what we have here. Plus, what is f of 2 times 1? So just f of 2. So this is going to be 2 times f prime at 2 is -1. F of 2, we were actually given that in the original stem there. So f of 2 is 6, so plus 6. So we have -2 plus 6, which is 4. So that's the derivative at 2. And then what is g of 2? G of 2 is going to be, remember, g is just x times f of x. So it's 2 times f of 2. So it's 2 times 6 there. So that's 12. So we have the point 2, 12, and we have a slope of 4. And so we can write our equation y minus the y coordinate, which is 12, equals our slope, 4 times x minus 2. If you wanted to write this and convert this into slope-intercept form, you could, and you would get y equals 4x plus 4. Okay. So in this graph, in this example, we are given the graph of the second derivative. So notice, this is the graph of f double prime. So the graph of the second derivative is shown at the right. Use this to answer each question. So when we do the test for concavity, because in part A it's asking us to determine where f is concave down. So when we do the test for concavity, we find that f is concave down when f prime decreases, but also when since we're considering the graph of f double prime, this is when the second derivative is negative. So when is the second derivative less than 0? So basically, when is it below the x-axis? So we can see that that happens there and there. So those x values are, this is -2 to 1, or -1, sorry, and then from 1 to 2. So our graph f is going to be concave down when this curve is below the x-axis, and that happens from -2 to -1, and then from 1 to 2. And then part B is asking, when is f prime increasing? So f prime increases. So if f prime is increasing, remember by definition, that means that f is concave up. And f is concave up when the second derivative is positive by the test for concavity. So when f is increasing, that means that our original function, when f prime is increasing, by definition, that tells us that f is concave up. And through the test for concavity, that happens, f is concave up when the second derivative is positive. So the second derivative is positive in these regions here. So here and this part here, and then that part there. So that's for all values of x that are less than -2. So that's going to be from -infinity to -2. From in between -2 and 2. So from -2 to 2. And then for values of x that are greater than 2. So from 2 to infinity. So those are the intervals where the function is increasing. All right. And last example. So in this one, it's asking us, ultimately, we're going to have to sketch a graph, but we're given a table of values. So let's kind of read what we are given in this problem. So it says, let f be a function that is continuous, so f is continuous, on the interval from the half-open interval from 0 to 4. F is twice differentiable except at x equals 2. So at x equals 2, you can see that the derivative does not exist. The function f has derivatives, and its derivatives have the properties indicated in this table. Again, where d and e indicates that the derivative of f does not exist at x equals 2. Okay, so we have this half-open interval from 0 to 4 that we have to try and answer some information about. So in part A, we're told for x between 0 and 4, find all values of x. So we're just looking for the x values, all values of x, at which f has a relative maximum or minimum, right? Relative extremum. So we find relative extremum. Remember, if you recall, relative extremum happens when f prime changes signs. So a sign change in the derivative indicates that we have a relative extremum. So where does f have a relative maximum or relative minimum? So where are there sign changes in the derivative? So we're looking at the derivative here, and we want to look at sign changes. So we have a positive region from 0 to 1. It's still positive from 1 to 2, so there's no sign change, even though there's a horizontal tangent, right? So the value of my derivative at 1 is 0. My graph is probably doing something like this, where it goes increasing and then continues to increase at that point. We have a sign change here at x equals 2. So x equals 2 is going to be a relative extremum. And then again, it goes negative to negative, so there's no sign change. So there's one sign change in the derivative, and it's at x equals 2. So x equals 2. And is it a relative max or min? So because the derivative changes sign from positive to negative, it is a relative maximum. X equals 2 is a relative maximum because f prime changes from positive to negative at x equals 2. All right, so that would be our justification there. So in part B, it asks us to graph f, sketch a graph of f. So to start this, I'm actually going to just plot the points that we know, right? So we're given 4 points, and then we're given some information about the first and second derivative. So let's plot the first 4 points. So when x is 0, y is -1. When x is 1, y is 0. When x is 2, y is 2. So we're up here. When x is 3, y is 0. So we know this information here. Okay. So we want to consider, so with the first derivative, that tells us about whether our function is increasing and decreasing. If the first derivative is positive, then f is increasing on those intervals. If it's negative, then it decreases on those intervals. So we can see that my function is going to be increasing on the interval from 0 to 2. Now, the real question is about concavity. So am I increasing like this, right? Or am I increasing like straight up like this? So the second derivative is going to help us determine concavity. So because my second derivative is negative on the interval from 0 to 1, that tells me that it's concave down. So concave down looks something like this, or some portion of that graph. So I believe we'll be concave down like this here. And And I know that at x equals 1, my first derivative is 0. So I have a horizontal tangent line there. So it's going to be concave down. We're going to have a horizontal tangent line there. It's still increasing in that region. But then from 1 to 2, my function is, my second derivative is positive, which means that it's concave up. So I'm going to have some region that's concave up, like this portion. So it's going to do something like this here. So we have a horizontal tangent there at 1. This part from 0 to 1 is concave down. This part from 1 to 2 is concave up. And we look like this. Okay. So we have that half of the graph. My derivative doesn't exist at 2, so I'm guessing we're going to have some sort of sharp point because the function is defined there, so it's not because of a discontinuity. So I'm guessing it's probably going to be because of some sort of sharp point. From 2 to 3, my second derivative is negative, and my first derivative is negative. So this first derivative being negative tells me I'm decreasing. Second derivative tells me I am concave down, right? Concave down. So it's going to be something like this, perhaps. My second derivative here is 0. That doesn't really matter too much to me right now. But I still know that I'm decreasing. I'm decreasing on the interval from 3 to 4, but that I'm positive on that interval, which means I'm concave up there. So after I cross through the x-axis here, my function changes to be concave up. So it's going to do something like this. We don't actually know the final value at x equals 4, so I just can... and it's not defined there, so I should have an open circle at 4, something like this. So my function would look perhaps something like that. It's concave up here because the second derivative, concave down here because the second derivative is negative, concave up here because it's positive. It increases on this entire interval because the first derivative is positive there. The first derivative is negative from 2 to 4, so that's why it's decreasing on that entire interval. And then it's negative here, so it is concave down. It's positive here, so it is concave up.